Today I'll be presenting VoxelNet end-to-end learning for point cloud-based 3D object detection, published at CVPR 2018 by Zhou and Oncel Tuzel from Apple. This paper proposes a unified end-to-end trainable network that simultaneously learns feature representations from raw LiDAR point cloud and prediction-accurate 3D bounding boxes without any handcrafted feature engineering. Here is the roadmap for today's talk. We will start with the motivation and problem setting and briefly cover related work. The bulk of the presentation covers the VoxelNet architecture, the voxel feature encoding layer, the convolutional middle layers, and the region proposal network. We will then look at the loss function, the efficient GPU implementation, and the training and the data augmentation details. Finally, we will go through the experiment results at the KITTI benchmark and close with a discussion and conclusion. Let's start with the motivation. LiDAR sensors are a key component in autonomous driving because they provide reliable metric depth information that cameras simply cannot match. We get accurate 3D localization and shape characterization regardless of lighting conditions. However, LiDAR point clouds comes with a fundamental challenge. They are sparse and point density is high variable. Objects close to the sensor have thousands of returns, while distant objects may have only a handful. This irregularity makes it difficult to directly apply standard convolutional neural networks (CNN), which expect dense grid structure inputs. Prior work addressed this by projecting points onto 2D grid or encoding voxels with handcrafted statistics. The authors argue these manual design choices create an information bottleneck. The network never sees the raw 3D geometry. Recall that in image-based detection, moving from handcrafted HOG features to learned CNN features was the key breakthrough. VoxelNet aims to do exactly the same for point cloud. The goal is a single end-to-end trainable network that learned both the feature representation and the detector jointly. These are three main families of prior methods. The first is a projection-based approaches, methods like VeloFCM project. Project the point cloud onto a cylindrical or bird's-eye view image and then apply standard 2D convolutions. The problem is that the projection discards intrinsic 3D shape information. The second family is voxel-grid method with handcrafted features. These rasterize the point cloud into a 3D voxel grid and encode each voxel with statistical quantities such as the mean, standard deviation, or binary occupancy. The MV method by Chen, which is the main baseline here, belongs to this group. Again, the manual feature choice is the bottleneck. The third family is point-based learning. PointNet and PointNet++ learn features directly from raw point set using shared MLPs and max poolings. These are impressive, but they were designed for classification tasks on datasets with roughly 1,000 points. A single LiDAR sweep contains around 100,000 points. Scaling PointNet-style architectures to that regime, while also performing detection, is the core challenge VoxelNet addresses. VoxelNet bridges the gap. It applies PointNet-style features in learning inside each voxel. then use a region proposal network on the resulting volumetric feature map. VoxelNet consists of 3 function blocks, which you can see in this figure. The first block is the feature learning network. It takes the raw point cloud, partition space into equally spaced 3D voxels, and applies stacked voxel feature encoding layers to transform the point within each voxel into a fixed length vector. The output is a sparse 4D tensor. The second block is the convolutional middle layers. These are standard 3D convolutions that aggregate spatial context across the neighboring voxels, progressively expanding the receptive field. They transform the sparse 4D tensor into a standard 3D feature map. The third block is the regional proposal network, or RPM. It consumes the feature map and produces 2 outputs, a probability score map telling us where objects are, and the regression map encoding the precise 3D bounding box parameters. Crucially, all 3 blocks are trained jointly end-to-end with a single loss function. There's no separate pre-training, or post-processing stage. Let me walk through the feature learning network in details. Step 1 is voxel partition. The 3D space is divided into equally spaced voxels of size Vd by Vh by Vw meters. For car detection, the authors use 0.4 by 0.2 by 0.2 meters, given a grid of 10 by 400 by 352 voxels. Step 2 is a grouping and random sampling. Each point is assigned to its voxel. Because density varies enormously, voxels with more than t points are randomly subsampled to exactly t points. For cars, t equals 35. This serves 2 purposes. It bounds the computation, and it reduces the sampling bias caused by variable point density. Step 3 is the stack VFE layers. Each point is represented as a 7-dimensional vector, its XYZ coordinates, and reflectance R plus the offset from the voxel centroid in X, Y, and Z. This centroid offset encodes the relative position within the voxel. The 7-dimension input is passed through a shared fully connected network consisting of a linear layer, batch normalization, and ReLU. An element-wise max pooling aggregates information across all points in this voxel into a single voxel level feature. That voxel feature is then concatenated back onto every point feature, so each point is now aware of a global voxel context. Stacking multiple such layers allows the network to learn increasingly complex 3D shape descriptors. The final output is a sparse 4D tensor of size C by D prime by H prime by W prime. Where only the non-empty voxels carry information, since over 90% of voxels are empty, these sparse representation yields major memory and compute savings. The VFE layer is the key innovation of this paper, so let me emphasize what makes it powerful. The critical design choice is a combination of point-wise features with a locally aggregated voxel feature. After max-pool aggregation, the voxel feature summarizes the entire local neighborhood. Concatenating it back to each point features means every point can now interact with every other point in the same voxel through this shared bottleneck. This is interpoint interaction, something a planned shared MLP without a pooling concatenation step cannot achieve. Stacking two VFE layers, VFE1 from 7 to 32 dimensions and VFE2 from 32 to 128 dimensions, followed by a final FCN mapping to 128 dimensions, gives the network enough capacity to learn descriptive shape information for the detection task. Compare this to PointNet. PointNet is applied globally to all points at once, typically around 1000, which is computationally feasible for object classification but not for detection over a full LiDAR sweep of 100,000 points. VFE restricts the interaction to within each small voxel, drastically reducing computation while still capturing local geometry. All voxels share the same MC and weight, so the approach is both parameter efficient and fully parallelizable across voxels. After the feature learning network, we have a sparse 4D sport tensor of shape 122 by 10 by 400 by 352. The convolutional middle layers process this with three sequential 3D convolutions. The first convolution has stride 2 in the depth dimension, which collapses the depth axis. After 3 layers, the output is a 4D tensor of size 64 by 2 by 400 by 352, which is then reshaped into a 2D feature map of size 128 by 400 by 352. This reshape is what connects the 3D feature volumes to the 2D RPM. The RPM takes this feature map and processes it through 3 blocks of fully convolutional layers. The first layer of each block downsamples by half using stride 2. Each block then applies multiple stride 1 convolution to refine feature within that scale. All 3 block output are unsampled to the same spatial resolution and concatenated to form a high-resolution multi-scale feature map. The concatenated map is passed to 2 heads, a classification head producing a score map, and a regression head producing a 7-dimensional bounding box residuals. The RPM is directly adapted from faster RCNN, but modified to operate on a 2D feature map derived from a 3D voxel grid, which is a non-trivial adaptation. The loss function combines classification and regression. A 3D ground truth box is parameterized by its center XYZ, its dimension, length, width, height, and its yaw angle theta. Anchors are placed on the feature map at two orientations, 0 and 90 degrees. The regression target is a 7-dimensional residual vectors. The center offsets delta x and delta y are normalized by the diagonal of the anchor base, dA, rather than the individual dimensions. This is a departure from previous work and makes the normalization invariant to aspect ratio. The delta z offset is normalized by the anchor height. The dimension residuals use log space encoding, and the angle residuals is a direct difference. The total loss has 3 terms. The first 2 are normalized binary cross-entropy losses for positive and negative anchors respectively, weighted by alpha and beta. The third term is the smooth L1 regression loss over positive anchors only. Setting alpha to 1.5 and beta to 1 gives more weight to the positive classification loss, which is appropriate given the large imbalance between positive and negative anchors. A major practical contribution of this paper is making the VFE computation efficient on a GPU. The problem is that GPUs are optimized for dense tensor operations, but the raw point cloud is inherently sparse with a variable number of points per voxel. The solution is a voxel input feature buffer, a pre-allocated dense tensor of shape k by t by 7, where k is the maximum number of non-empty voxels and t is the maximum number of points per voxel. The algorithm iterates over the point cloud exactly once, O of m complexity. For each point, it uses a hash table with the voxel coordinate as the key to look up the voxel in O1. If the voxel exists and has fewer than t points, the point is inserted. If the voxel is full, the point is discarded. This is exactly the random sampling step. If the voxel doesn't exist yet, a new entry is created. Once the buffer is constructed, OVFE operations are dense matrix multiplication and element-wide operations which execute in parallel across OK voxels and OT points simultaneously on the GPU. After VFE, features at empty point positions are zeroed out, so they don't affect the max pool aggregation. Finally, the computed voxel features are scattered back to the positions in the dense 3D grid using a stored coordinate buffer and the standard 3D convolutional and RPN follow. The total inference time on a Titan X GPU is 225 milliseconds, with the convolutional middle layers taking the majority of 117 milliseconds. For car detection, the input range covers 17.4 meters forward, 80 meters laterally, and 4 meters in height. Voxels are 0.4 by 0.2 by 0.2 meters. For pedestrian and cyclist detection, the range is smaller, 48 by 40 meters, and T is increased to 45 to capture more points for these smaller, hard-to-detect objects. For pedestrians and cyclists, the first RPM blocks use stride 1 instead of stride 2, given finite anchor resolution to better handle their smaller footprint. Data augmentation is critical here because a KITTI training set has fewer than 4,000 samples, far too few to train a deep neural network from scratch without regularization. Three strategies are applied. The first is per box perturbation. Each ground truth box and the LiDAR points inside it are independently rotated by a random angle up to 18 degrees around the z-axis and translated by a Gaussian offset with a standard deviation 1 meters. A collision test is run after perturbation, and any physically impossible configurations is reverted. The second strategy is global scaling. The entire point cloud and all bounding box are scaled by a random factor drawn uniformly from 0.95 to 1.05. This simulates objects at varying distances. The third strategy is global rotation. The entire scene is rotated around z-axis by up to 45 degrees, simulating the the eagle vehicle making a turn. All three augmentation are applied on the fly in Python with negligible computation, so no extra storage is needed. Training uses SGD with a learning rate of 0.01 for 150 epochs, decayed by 0.001 for the final 10 epochs, and a batch size of 16 point clouds. All experiments are on the KITTI 3D object detection benchmark, which is the standard dataset for autonomous driving perception. It provides 7,481 labeled training samples and 7,518 test samples covering three object classes: car, pedestrian, and cyclist. Each class has three difficulty levels: easy, moderate, and hard, determined by the object size in the image, its occlusion level, its truncation level, and that's it. The evaluation metric is average precision, or AP. The IOU threshold is 0.7 for car, 0.5 for pedestrians and cyclists, applied identically in bird's eye view and full 3D evaluation. Following the standard protocol from prior works, the authors split the training data into 3,712 training samples and 3,769 validation samples, ensuring no sequence overlap between the two splits. The hard-crafted baseline HC baseline uses the sample RPN architecture as the VoxelNet, but replaces the feature learning network with pre-computed bird-eye view features at 0.1 meter resolution with 16 height channels, and replaces the 3D convolutional middle layers with equivalent 2D layers. The total parameter count as similar to VoxelNet. This controlled comparison directly isolates the contribution of end-to-end feature learning. Importantly, VoxelNet is trained entirely from scratch using only LiDAR data, which competing methods such as Mono 3D, 3DLP, and MV use ImageNet pre-trained models for initialization. Let's look at the bird's eye view detection results on the KITTI validation set. VoxelNet outperforms all competing methods across all three classes and all three difficulty levels. The car classes VoxelNet achieved around 89.6, 84.8, and 78.6 AP at the easy, moderate, hard, compared to the best prior LiDAR method, MV with BV plus FV plus RGB, which reaches inferior results. Note that MV uses both LiDAR and an RGB camera, and it is initialized from a pre-trained model. Yet, VoxelNet surpasses it with LiDAR alone and training from scratch. The HC baseline also does well on car, which confirms that RPN design is strong, but for pedestrian and cyclists, the gap between VoxelNet and HC baseline opens up significantly. VoxelNet leads by roughly 9% points respectively on the moderate difficulty. This tells us that for smaller, more shape-diverse objects, the end-to-end learned features are essential. Handcrafted bird's eye view projections are simply not expressive enough. Now for the more challenging full 3D detection task. Well, the IOU is computed in 3D space rather than in bird's eye view plane. The gains of VoxelNet over MV on the car class are substantial, plus 10.7, plus 2.8, and plus 6.3 percentage points on easy, moderate, and hard. Keep in mind, MV uses an additional RGB camera and a pre-trained backbone, which is particularly telling. It's a comparison between VoxelNet and HC baseline. In bird's eye view, the improvement for pedestrian was around 7 to 8 percentage points. In full 3D detection, it grows to approximately 12 percentage points. The reason is that accurate 3D detection requires precise localization in all 3D dimensions, not just a 2D ground plan. This demands a feature representation that truly captures 3D shape, exactly what stacked VFE layers learn, handcrafted features which essentially project hide information into channels, lose the fine-grained 3D structure, and therefore suffer more in the full 3D task. On the official KITTI task server, VoxelNet again outperformed the previously published state-of-the-art across all task categories, the difficulty levels, of course. For the car class, it achieves far better results. For pedestrian cyclists, it gained over prior LiDAR-only methods are even more pronounced, consistent with the validation set findings. The qualitative examples on the right shows VoxelNet detections projected back onto the RGB image for visualization. You can see tight, well-oriented 3D bounding boxes around cars, pedestrians, and cyclists. Objects that vary significantly in size and point cloud density. The detector handles all three categories reliably, which demonstrates the generality of the learned voxel feature representation. Let's take a closer look at the ablation comparing VoxelNet to HC baseline, since this is a key experiment that justifies the end-to-end design. The HC baseline is a carefully constructed strong baseline. It uses the same RPM, similar parameter count, and the same training procedure, and the same data augmentation. The only difference is the feature representation. Handcrafted bird's eye view features versus learned VFE features. This isolates the impact of end-to-end feature learning. The results shows that for car class, where the object is large, box-shaped, and easy to distinguish in bird's eye view, the HC baseline performs reasonably well. Handcrafted features capture enough information for this relatively simple geometry. For pedestrian and cyclists, however, the story changes dramatically. These objects are small, have complex and variable 3D shapes, a person walking versus a cycling with a bike, and their footprint in bird's eye view provides little discriminative information. The VFE layers learn to encode the full 3D structure with each voxel. Given the network the shape information it needs, the improvement is roughly 12 to 13 percentage points of 3D detection for these categories. The clear message is end-to-end features learning matters most when the task requires fine-grained 3D shape understanding. To summarize, VoxelNet makes three core contributions. First, Voxel Feature Encoding layer, a novel, learnable encoders that enable inter-point interactions within a voxel-scaled point net style, feature learning to full LiDAR sweeps of 100,000 points. Second, a complete end-to-end architecture combining stacked VFE layers, 3D convolutional middle layers, and the regional proposed Zhou network, all trained jointly from a single loss. Third, an efficient GPU implementation based on hash table voxelization and a pre-allocated dense buffer that makes the system practical at 225 milliseconds per frame. The experimental result on KITTI demonstrates state-of-the-art performance for LiDAR-only 3D detection across all three classes, outperforming even methods that use an additional RGB camera. The authors point to several directions for future work: joint LiDAR and image-based end-to-end detection to fully improve accuracy, a box refinement subnetwork, and a multi-class supervision to resolve ambiguity between similar categories such as pedestrians and cyclists. VoxelNet established an important paradigm: treat point clouds as first-class representation and let the network learn how to encode them, just as convolutional networks learn how to encode images. Thank you.